Imagine falling toward the edge of a black hole. To observers watching from a safe distance, you appear to slow down, freeze, and fade away at the event horizon, suspended there forever. But from your perspective, you cross the event horizon in finite time and plunge toward the singularity. Both perspectives are correct. Both are real. This isn't science fiction. This is the paradox that sits at the heart of our understanding of space-time itself. A paradox that, when examined closely, suggests something profoundly disturbing about the nature of reality. Some physicists now believe that black holes aren't simply massive objects that trap light. They may be cosmic horizons, where the laws of physics themselves fracture into irreconcilable truths. What if you could exist in two fundamentally different states simultaneously? What if the universe doesn't have one consistent story about what happens, but multiple contradictory ones, all equally valid? Today, we journey through evidence that challenges everything we thought we knew about time, space, and the continuity of physical law. Prepare yourselves. We begin. Act 1. The Discovery. In 1915, just months after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild was serving on the Russian front during World War I. Between artillery barrages, he did something extraordinary. He found an exact solution to Einstein's field equations, the first person ever to do so. What Schwarzschild discovered was mathematically elegant but physically bizarre. His solution described what would happen if you compressed enough mass into a small enough space. There would be a radius, now called the Schwarzschild radius, where space-time curves so severely that it folds in on itself. Nothing that crosses this boundary can ever escape. Not matter, not light, not information itself. Einstein was disturbed by the solution. He thought it represented a mathematical quirk, not physical reality. Surely, he reasoned, nature wouldn't permit such monstrosities to exist. He was wrong. For decades, black holes remained theoretical curiosities. But in 1964, everything changed. A rocket-mounted X-ray detector scanned the constellation Cygnus and found something impossible. An intense X-ray source flickering wildly, pumping out more radiation than 1,000 suns, yet concentrated in a region smaller than Earth. Scientists named it Cygnus X1. The measurements revealed an invisible object with at least 10 times the mass of the Sun orbiting with a visible blue supergiant star. The invisible companion was pulling material from its partner, heating it to millions of degrees before it vanished forever beyond an invisible boundary. The first black hole had been found. But here's where the real mystery begins. As physicists studied the mathematics more carefully, they discovered something deeply troubling about what happens at that boundary, the event horizon. The equations revealed a fracture in reality itself. Think of space-time not as empty nothingness, but as a fabric that can be stretched, compressed, and warped by mass and energy. Near a black hole, this warping becomes extreme. Time itself slows down as gravity intensifies. This isn't metaphorical. Clocks literally tick slower in stronger gravitational fields. GPS satellites orbiting Earth must account for this effect, or they'd accumulate errors of several kilometers per day. Now imagine taking this time dilation to its limit. As you approach a black hole's event horizon, time from an outside observer's perspective slows dramatically. If you were falling toward a black hole and I watched from a safe distance, I would see you moving slower and slower as you approach the horizon. Your image would redshift, your movements would appear to freeze, and eventually, you would seem to stop completely at the event horizon, frozen there forever. But from your perspective, something completely different happens. You don't slow down at all. You cross the event horizon in a matter of seconds or minutes, depending on the black hole's size. Time for you continues normally. You pass through the horizon and continue falling toward the singularity at the center. Both descriptions are accurate according to general relativity. The mathematics supports both perspectives, but they're mutually exclusive stories about the same event. This is called the horizon complementarity problem, and it gets stranger. In the 1970s, Stephen Hawking discovered that black holes aren't truly black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation. Over incomprehensibly long timescales, this radiation causes black holes to evaporate completely. Here's the paradox. That radiation appears to be completely random, carrying no information about what fell into the black hole. But quantum mechanics has an iron law. Information cannot be destroyed. It can be scrambled, encrypted, or hidden, but never erased from the universe. So what happens to the information carried by everything that falls into a black hole? Does it disappear, violating quantum mechanics? Or does it somehow escape, violating general relativity's promise that nothing can leave a black hole?
This is the black hole information paradox. For nearly 50 years, it has forced physicists to confront an uncomfortable possibility that our two most fundamental theories, quantum mechanics and general relativity, are incompatible at black holes. They cannot both be completely correct. But the evidence forces us to confront an uncomfortable possibility that reality itself may not be singular and consistent, but instead depends fundamentally on perspective in ways that shatter our notion of objective truth. Act 2. Accumulating Evidence. Part A. Observable Signatures. From 1500 to 2500. Let's examine what observations actually tell us about black holes and the nature of their boundaries. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, a supermassive monster 55 million light-years away at the center of the galaxy M87. The black hole contains 6.5 billion times the mass of our Sun. The image showed a glowing ring of light surrounding a dark circular void, approximately 38 billion kilometers across. That image confirms something crucial. The event horizon is real and exactly where general relativity predicts it should be. Matter orbiting just outside the horizon reaches incredible speeds, a significant fraction of light speed, and temperatures exceeding 10 billion degrees. Yet the horizon itself remains invisible, a perfect sphere of absolute darkness. But the evidence forces us to confront an uncomfortable possibility, that reality itself may not be singular and consistent, but instead depends fundamentally on perspective in ways that shatter our notion of objective truth. In 2020, researchers analyzing data from the Neutron Star and Black Hole Observatory NICER detected something extraordinary in the X-ray emission from a stellar mass black hole called MAXI J1820 plus 070, located about 10,000 light-years from Earth. The flickering wasn't random. It showed quasi-periodic oscillations, rhythmic variations in brightness occurring hundreds of times per second. These oscillations corresponded to matter orbiting at the innermost stable circular orbit just outside the event horizon, where gravity is so intense that orbits become unstable. What's remarkable is this. The mathematical analysis revealed that space-time itself is being dragged around the black hole like water swirling down a drain. This is called frame dragging, or the lens-theoring effect. Near the event horizon, space isn't just warped, it's being physically pulled around the black hole's rotation. This means there's a region near the horizon called the ergosphere where it's literally impossible to stand still. Space itself is moving faster than light relative to distant observers. You would be swept along whether you fired your rockets or not. In 2022, astronomers using the Chandra X-ray Observatory studied a black hole at the center of a galaxy cluster called SPT CLJ 2344343, located 5.9 billion light-years away. They discovered something that challenges our understanding of what happens at the event horizon. The black hole was actively feeding, consuming vast amounts of material. Yet the X-ray observations revealed energy jets erupting from near the black hole's poles with velocities exceeding 99.9% of light speed. These jets extended for hundreds of thousands of light years into intergalactic space. Here's the puzzle. The energy powering those jets apparently comes from the rotational energy of the black hole itself, through a process called the Blandford-Znaiec mechanism. Magnetic field lines threading through the event horizon can extract energy from the black hole's rotation and funnel it into the jets. But this requires something peculiar. The magnetic field lines must, in some sense, cross the event horizon. Information about the black hole's rotation must in some way escape the event horizon to power the jets. Yet general relativity insists that nothing can escape.
The resolution involves quantum effects and the detailed structure of space-time near the horizon. But it hints at something profound. The event horizon is not a simple one-way membrane. It's a far more complex boundary where quantum and gravitational effects intertwine in ways we don't fully understand. But this represents just one piece of a much larger puzzle. The evidence from gravitational wave observatories has opened an entirely new window into what happens when black holes collide and what those collisions reveal about the nature of the horizon itself. Part B. Deeper Implications. On September 14th, 2015, the LIGO gravitational wave detectors felt space-time itself ripple as two black holes, each roughly 30 times the mass of the Sun, collided 1.3 billion light-years away. The merger released more power than all the stars in the observable universe combined, radiated not as light, but as gravitational waves. Since then, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Each one provides precise measurements of black hole masses, spins, and the detailed gravitational waveforms produced during collision. Here's what makes these observations extraordinary. The gravitational waves match Einstein's predictions with stunning precision. The waveforms show exactly what general relativity says should happen when two event horizons merge. The signal starts with the black holes spiraling inward, accelerates through the merger, and then rings down as the combined black hole settles into a stable state. But in 2020, researchers analyzing the merger event GW190521 discovered something unexpected. This merger involved the most massive black holes ever detected by LIGO, 85 and 66 solar masses. The combined mass of 142 solar masses placed the resulting black hole firmly in a mass range that theoretical models say shouldn't exist through stellar evolution. The observations suggest these black holes might have formed through previous mergers, creating hierarchical growth. But it also revealed something peculiar in the gravitational wave signal. Subtle anomalies in the ring-down phase that some physicists believe might indicate exotic quantum effects at the event horizon. The most remarkable discovery involves what happens in the final moments before two event horizons touch. Numerical simulations, the most sophisticated ever run, model the collision down to the Planck scale, where quantum effects should dominate. These simulations reveal that in the infinitesimal moment when two event horizons make contact, the geometry of space-time undergoes a topological transition. The two separate horizons merge and form a single, larger horizon. But in that transition moment, the mathematics suggests something radical. A brief moment where the space-time geometry cannot be described by smooth, continuous curves. The geometry develops what mathematicians call a singularity. Not the singularity at the black hole's center, but a singularity in the event horizon surface itself. For a fraction of a second, shorter than any measurable time, the structure of space-time at the horizon becomes undefined by general relativity. What happens in that moment? General relativity cannot tell us. The equations break down. This is precisely where quantum gravity, a theory we don't yet have, should take over. Recent theoretical work has revealed something even stranger. In 2019, physicist Ahmed Almiri and colleagues proposed a resolution to the information paradox called the island formula. The mathematics suggests that information falling into a black hole isn't destroyed or trapped permanently. Instead, it's encoded in quantum correlations that extend beyond the event horizon in a way that doesn't violate general relativity. This proposal requires something radical. The interior of a black hole is not separate from the exterior. They're quantum mechanically entangled in a way that makes the entire notion of inside and outside somewhat illusory. Think about that. The event horizon, the boundary we've been discussing as the point of no return, might not be a boundary in the traditional sense at all. It might be more like a quantum interface where information is simultaneously inside and outside, depending on how you measure it. This isn't just theoretical speculation. Recent experiments with quantum computers have successfully simulated simplified versions of black hole dynamics. In 2022, researchers at Google and Caltech used a quantum processor to simulate the behavior of information near a black hole horizon. They observed quantum scrambling, the rapid spread of quantum information that matched theoretical predictions. The evidence extends beyond black holes themselves into the realm of quantum information theory and suggests that black holes might be the universe's most efficient information processors, scrambling data faster than any other physical system.
But perhaps the most mind-bending evidence comes from holographic theory. Starting in the 1990s, physicists realized that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional surface surrounding that volume, like a hologram. For black holes, this means that everything that falls into a black hole, all its information, is somehow encoded on the event horizon surface. The interior might not contain independent information at all. The three-dimensional interior could be an emergent description of information fundamentally stored on the two-dimensional horizon. If true, this suggests something profound about the nature of space itself. The universe might not be fundamentally three-dimensional. Space itself could emerge from quantum information encoded on boundary surfaces, with black hole horizons serving as the ultimate proof of concept. The evidence extends beyond black holes into the realm of quantum gravity, and suggests that space-time itself is not fundamental but emergent, constructed from something deeper. Act 3, the big picture. Part A, theoretical framework. So how do physicists make sense of these paradoxes? What theoretical framework can accommodate both the relativistic picture of frozen horizons and the quantum mechanical requirement that information escapes? The answer being developed by theoretical physicists is radical. Black holes are not primarily gravitational objects. They're quantum mechanical objects that happen to have strong gravitational effects. The event horizon is not a place in space, but a quantum state, a configuration of quantum information. This perspective is called the firewall proposal, and its implications are staggering. According to this idea, the smooth, empty space at the event horizon that general relativity predicts doesn't actually exist. Instead, an infalling observer would encounter a wall of high-energy particles right at the horizon, a firewall that incinerates anything that approaches. This violates Einstein's equivalence principle, which states that freefall should be indistinguishable from floating in empty space. At the event horizon of a large black hole, you shouldn't feel anything special as you cross. The tidal forces would be gentle and you'd sail through smoothly. The firewall proposal says that's wrong. You would die instantly upon reaching the horizon, burned by quantum radiation. Why would physicists propose something so radical? Because saving quantum mechanics seems to require it. If information escapes a black hole through Hawking radiation, then that radiation must be quantum mechanically correlated with everything that previously fell in. But maintaining those correlations while also preserving the smooth horizon predicted by general relativity creates contradictions in the quantum mathematics. Something has to give, either quantum mechanics, general relativity,
or our notion of a single consistent description of reality. Many physicists now work on alternatives to the firewall, but they're equally radical. String theory, our best candidate for quantum gravity, suggests that black holes are constructed from fundamental strings and membranes vibrating in higher dimensions. The event horizon emerges from collective behavior of vast numbers of quantum strings, much like temperature emerges from the motion of molecules. In this picture, asking what happens at the event horizon is like asking what happens to temperature at a single molecule. The question is ill-posed because the phenomenon only exists at a larger scale. This forces us to reconsider fundamental assumptions about space and time. If horizons are quantum states rather than geometric surfaces, then spacetime itself might be quantum, constructed from discrete granular building blocks at the Planck scale of 10 to the negative 35 meters. Several approaches to quantum gravity, loop quantum gravity, causal set theory, emergent gravity, propose exactly this. Spacetime is not smooth and continuous, but made of elementary units connected in a vast quantum network. Black holes would then be regions where this network has a particular configuration that creates the macroscopic appearance of a horizon.
The philosophical implications are profound. We think of space as the arena where physics happens, and time as the dimension along which events unfold. But if space and time emerge from quantum information, then they're not fundamental. Reality at its deepest level might be informational, not physical. The universe might be more like a cosmic computation than a mechanical system. Part B. Future implications. So where does current research stand, and what observations might resolve these paradoxes? The Event Horizon Telescope is now targeting Sagittarius A star, the supermassive black hole at our galaxy's center, just 26,000 light-years away. Images of this black hole could reveal fine details of the event horizon structure and test whether quantum effects create detectable deviations from general relativity's predictions. The next generation of gravitational wave detectors, LIGO A+, the Einstein telescope, and the space-based LISA mission, will detect black hole mergers with unprecedented precision. They'll measure the detailed ring-down signals as merged black holes settle into their final state. These signals carry information about the event horizon structure and could reveal quantum corrections to general relativity's predictions. Recent breakthroughs suggest we might even detect something remarkable: black hole echoes. If quantum effects create structure near the horizon, gravitational waves might partially reflect off that structure before escaping. This would create faint echoes in the gravitational wave signal milliseconds after the main event. Researchers analyzing LIGO data claim to have found hints of such echoes, though the evidence remains controversial. If confirmed, echoes would be the first direct evidence that event horizons have quantum structure. Theoretical work is advancing rapidly too. In 2022, researchers made progress on calculating how information escapes from black holes using replica wormholes, mathematical constructions that connect the black hole interior to the Hawking radiation. The calculations suggest that information does escape, but in a deeply scrambled form that requires collecting essentially all the Hawking radiation to decode. This means that if you wanted to reconstruct what fell into a black hole, you need to wait until the black hole almost completely evaporated, a time so long that it vastly exceeds the current age of the universe for any astrophysical black hole. From any practical perspective, the information is lost, even though it's preserved in principle. But the mathematics also reveals something remarkable. The interior of an old evaporating black hole becomes quantum mechanically connected to the exterior through these replica wormholes. The black hole interior and the cloud of Hawking radiation form a single entangled quantum system. The horizon doesn't separate them, it connects them. What this means for us comes down to a fundamental question. What is the nature of reality itself? If black holes teach us that reality depends on perspective, that different observers can have equally valid but contradictory experiences, then the universe is far stranger than classical physics imagined. There may not be one true story about what happens. Reality might be inherently perspectival, with different observers literally inhabiting different but equally real descriptions of events. This connects to broader questions in quantum mechanics about the role of observation in creating reality. The famous measurement problem asks why quantum superpositions collapse into definite states when observed.
Black holes amplify this question to cosmic scales. If an astronaut falls into a black hole, are they simultaneously frozen at the horizon from the outside and continuing through from their own perspective? Do both states coexist in some quantum sense? These aren't just philosophical puzzles. They're questions about the physical structure of reality that upcoming observations might actually answer. Within our lifetimes, we may know whether event horizons have quantum structure, whether information truly escapes black holes, and whether space-time itself is emergent. The most profound implications emerge when we consider that black holes might not be rare cosmic monsters, but fundamental components of how the universe works. Every time quantum fields create entanglement between distant particles, they may be creating microscopic structures analogous to black hole horizons, tiny bridges through space-time connecting the particles. Quantum entanglement might literally be constructing the fabric of space, with black holes representing an extreme case where the construction becomes macroscopically visible. Space itself could be stitched together by quantum information, and black holes could be the seams where we can see the stitching. If true, then understanding black holes isn't just about understanding exotic objects in distant galaxies. It's about understanding the deepest structure of reality itself, how space emerges from quantum mechanics, how time flows from information processing, and how the universe can support multiple equally valid perspectives on the same events.
Let's push these implications to their limits and confront what black holes might ultimately reveal about existence. Consider this thought experiment. Imagine two identical astronauts approaching a black hole. One falls in, crosses the event horizon, and experiences the interior before being destroyed at the singularity. The other fires their rockets and hovers just outside the horizon, watching their twin fall in. According to our current best theories, both astronauts' experiences are equally real. The hovering astronaut sees their twin frozen at the horizon forever. The falling astronaut crosses smoothly and experiences the interior. Neither perspective is more true than the other. They're complementary descriptions that cannot be simultaneously experienced, but are both part of reality. Now here's the disturbing part. If we take quantum mechanics seriously, both possibilities might exist in superposition until measured. The astronaut might be both frozen at the horizon and continuing through the interior until something, observation, decoherence, or some unknown process selects one reality. This suggests that reality itself might not have a definite state until observed. The universe might exist in a superposition of different histories, with black holes serving as natural laboratories where this quantum indeterminacy becomes macroscopically visible. The most profound implications emerge when we consider what black holes suggest about the fate of information in our universe. The holographic principle, the idea that all information in a volume is encoded on its boundary, might apply not just to black holes, but to the entire observable universe. Our cosmic horizon, the boundary beyond which we cannot see because light hasn't had time to reach us, might function exactly like a black hole horizon. All the information about the universe might be encoded on this boundary surface, with the three-dimensional space we experience emerging from that two-dimensional encoding. If true, this has stunning implications. We might be living inside what's effectively a cosmic hologram, with the fundamental description of reality existing on a distant boundary surface 46 billion light-years away. The depth and volume of space might be illusory, emergent phenomena arising from information fundamentally stored in two dimensions. Some physicists go further. Leonard Susskind has proposed that the universe itself might be fundamentally quantum computational, with physical laws arising from information processing. In this view, black holes are cosmic computers processing information at the maximum possible rate allowed by physics. This connects to an even deeper question. Why does the universe have consistent laws at all? If reality is fundamentally quantum mechanical and perspectival, why do different observers agree on physical laws even when they disagree on specific events? Black holes might provide the answer.
The mathematics of holography suggests that physical laws, the rules governing how information evolves, are constrained by consistency requirements across different perspectives. The physical laws might be the unique, self-consistent rules that allow multiple observers to have different experiences of events while still communicating and comparing observations. In other words, the laws of physics might exist because they're the only rules that allow multiple perspectives to coherently coexist. Black holes, by forcing us to confront incompatible perspectives, might be revealing the deep logical structure that underlies physical law itself. One final consideration. If black holes eventually evaporate completely through Hawking radiation, they leave behind only thermal radiation and gravitational waves. Where does the black hole go? More precisely, where do all the correlations, structures, and information that made the black hole unique end up? The current best answer is that they're encoded in subtle correlations in the radiation, so subtle and scrambled that extracting them would require impossible levels of precision. From any practical standpoint, the information is lost. The black hole's history is effectively erased from the universe. But quantum mechanics says information cannot be truly destroyed. So, perhaps information doesn't live in our universe alone. Perhaps evaporating black holes leak information into other universes, other branches of the quantum multiverse, or other structures we haven't yet imagined. The universe might be leaking. Black holes might be drains where information flows out of our cosmic domain into realms beyond our possible observation. We might be losing parts of our history to places we cannot reach or even conceptualize. Or perhaps the opposite is true. Perhaps information from other domains leaks into ours through quantum fluctuations, and black holes are actually places where information is being created rather than destroyed, welling up from deeper levels of reality we haven't yet discovered.
We began by confronting a paradox that observers falling into black holes and observers watching from outside experience fundamentally different realities, both equally valid according to our best theories. We've journeyed through decades of observations, X-ray telescopes revealing the fury of accretion disks, gravitational wave detectors measuring colliding horizons, quantum computers simulating information scrambling. Each piece of evidence has revealed that black holes are far stranger than Einstein imagined. They're not simply massive objects that trap light. They're boundaries where our classical intuitions about reality break down completely. The current scientific consensus is clear on some points. Black holes exist. Horizons are real. General relativity accurately predicts their large-scale behavior. Information is conserved, though we don't fully understand how it escapes. But on the deepest questions, whether horizons have quantum structure, whether space-time is fundamental or emergent, whether reality is truly perspectival, we remain uncertain. We stand at the edge of knowledge, looking into a conceptual abyss as deep as any black hole. Yet from this uncertainty comes something remarkable. Black holes are teaching us that the universe is not a mechanical system of particles bouncing around in empty space. It's something far more subtle and strange. A quantum information structure where observation and perspective play fundamental roles, where space and time emerge from deeper principles, and where reality itself might be more fluid and contextual than our intuitions suggest. We've learned that horizons mark boundaries not just of space, but of knowledge itself, limits beyond which even light cannot carry information, yet across which quantum mechanics insists that information somehow flows. We've learned that these contradictions aren't failures of our theories, but opportunities to discover deeper truths. The journey continues. New telescopes will image horizons in unprecedented detail. Gravitational wave detectors will catch the whispers of merging horizons. Quantum computers will simulate black hole dynamics. Theoretical physicists will continue to probe the mathematics of quantum gravity. And perhaps, in our lifetimes,
we'll witness the resolution of these paradoxes, the moment when humanity finally understands what happens at the edge of a black hole, and in doing so, learns what reality truly is. Until then, we're left with this profound truth. The universe has placed a limit on what we can know, but it has not placed a limit on what we can discover about that limit. Every horizon marks not an end, but a beginning, an invitation to look deeper, think harder, and expand our conception of what is possible. The universe is vast. The mysteries are endless. The journey continues.